Alrighty. Oh, let me get some more highlighters. Sorry. Remembering to leave out. Okay. Trying to think what highlighters I want.
Dina.
Just grab all of them. Where did the orange ones go? Alrighty. Okay. So, I didn't have this piece of paper the other day when we were talking about elimination reactions. So let me just kind of point them out to you guys again. I'm going to try to do some color coding. I used orange and I used yellow. So let's use green. Okay. So, I'll just quickly recap elimination reactions so that way we can then do addition reactions. So elimination reactions are when you're taking things out of the molecule. So for example, I have an alcohol and I'm removing an alcohol and a hydrogen to then form a double bond. There's always 2 carbons that are involved in that reaction because I need to take 1 from each. So this is my elimination reaction here. I'm just going to help you color code it. I'm just trying to help you guys. And then the other one we have is a haloalkane going to an alkene. So that's my elimination reactions. So elimination, we're talking about removing something from each of from 2 carbons, 2 neighboring carbons, in order to form a double bond. So elimination, we are removing things from an atom or group of atoms between 2 neighboring carbons to then make a double bond. So if I'm looking at my alcohol, this is a group of atoms, the OH. I'm removing that. I'm removing one of the hydrogens from a neighboring carbon to form a double bond. For the haloalkanes, I am removing a halogen and a hydrogen from a neighboring carbon and then forming a double bond. What you'll notice with these reaction schemes is that alkenes are very central to our reaction scheme. It's kind of like the city center of our map because there's a lot of things that can go along with the alkanes. Are we okay with that so far? All right. So the next thing that we're going to be talking about today then is addition reactions. So that's taking the alkene and breaking the double bond and adding stuff to it. So addition reactions are breaking the double bond to add stuff to it. So a lot of the namings make sense, and I'm trying to squish things in now. So breaking that C double bond C so we can add to the molecule. So we got lots of options for addition reactions here. So if I want to go from an alkene to an alcohol, we need acidified water. So that's an example of an addition reaction. All right. Something that I want to point out to you guys, that's a common question that they ask. You see how this is concentrated sulfuric acid where this is a dilute acid. So they often like to ask, okay, what is the difference in this reaction versus a concentrated versus dilute? So concentrated can go from alcohol to alkenes, and if I want to reverse that, I need dilute acid to do that. They often ask this question as a pair because they're very similar. They're both using acids, but at different concentrations. So don't be surprised if they ask you to do that comparison. Another addition reaction we could have is we could have the alkene being added to a hydrogen halide. So HX means you have one half is a hydrogen and then the X is a halogen. So again, we break the double bonds and now we go back to forming an haloalkane. So that's also another addition reaction. We could also take these alkenes and we can have hydrogen with nickel or platinum as a catalyst, and it needs heat, and we can go from an alkene to an alkane. Now, you guys do need to have these reactions memorized. They will not give you something like this on the assessment. So I will have a lesson when we get to that reaction scheme section, and I'll get some flashcards for you guys. Or you can start making your own flashcards. Okie dokie. The other thing I do with the alkenes is I can use bromine water, and again, I make a dibromo. So in this case, I am breaking the double bond and adding a bromine to each each carbon involved in the double bond. And this one, I'm only adding one. So that's the difference between these two. This is, note the difference here, that's only adding one halogen. This one is adding two. And then the last one of our addition reactions is, again, using that permanganate that we saw over here. We can use that and make a diol. So diol has two alcohol groups. All right, questions, concerns, or comments at this point? Are we okay? Next bit. Okay. So the other thing that we talked about when we were looking at this flow chart, actually this last bit here is going to be its own separate lesson, so don't stress about that last reaction. But one of the other things we talked about in our bit when we're talking about these different types of reactions is we also talked about identification tests. So how can we figure out something is something? So one of the things we have is how do we figure out an alkene is an alkene. These two here are actually identification tests on top of being addition reactions. So when I use bromine water, one of the things to note is that it starts as an orange color. And if there's a positive reaction, it goes colorless. Now we saw this before with the alkanes. The difference with this one is that this is going to be a fast reaction. And again, we'll look at it on the sheet, identification sheet. So we see that one over here. So fast reaction with bromine water to decolorize. So we can see that with any double bond or a triple bond. This is an addition reaction, so we see it going from orange to colorless. If it was an alkane, that reaction would still occur, except it will be very slow. So the key in that one is that it's going to be fast. So speed is another way that we can distinguish stuff. I'm just trying to find my black. We okay with that? All right, the next one, and I don't know if it's actually on there. I think it's probably listed it twice. Yes, it is. Okay. The next one, like I said, is that permanganate. That permanganate is a purple color. And it should go colorless if it's acidified. If it's not acidified, then I'll go brown. It only works with the permanganate. It doesn't work with the dichromate. It's not a strong enough oxidant. So that's another way we can test for an alkane. And don't worry, I will do a whole lesson on identification tests. I'm just pointing it out so you can start getting used to it. So, and I think we have it over here. So permanganate, colored solution, purple permanganate is rapidly decolorized by an alkene, making a diol. If there's no hydrogens, then you'll get a brown precipitate instead of colorless. It's an oxidation type of reaction. It could also be considered addition too. All right, are we okay with that? All right, let's keep moving then. Okay. So the next thing I want to talk about then is some unique types of addition reactions that might introduce some extra rules. So something we have to keep in mind is something called Markovnikov's rule. So just like with Zaytev's rule, we're talking about how do we add to unsymmetrical alkenes. In fact, Zaytev's rule, the other way it is known is anti-Markovnikov's rule. So FYI, you can hear Zaytev's rule being called anti-Markovnikov's rule because it's basically just the same thing in reverse. The reason why I decided to start with elimination reactions and then addition was because if I did addition second, then I could then tie in polymers, which is going to be our next lesson. So that was kind of my thought process. So let's look at the exam question that I have and then use that as a means to kind of explain Markovnikov's rule to you guys. So we are looking at the addition, so this is from the 2021 exam. It's question 1C. I think I've attached this onto Google Classroom if you guys want to type your notes. I can't quite remember if I was smart enough to do that. But they talk about two compounds here, and they're asking which of these two is going to do Markovnikov's rule and which one is not, and explain the reasons why. I'll show you Markovnikov's rule, and then I'll show you why the second molecule doesn't do Markovnikov's rule. So molecule number 1 does do Markovnikov's rule. So let's work our way through it. So I'm just copying it down on my piece of paper and I'll switch it over. So you have CH2 double bond CH, CH2, CH3. I will also draw it out expanded just so you guys can see it that way too. All right, nice little refresher. Does this one form geometric isomers? Yay or nay? Thumbs up or thumb down? Yes, it does form geometric isomers. Thumbs down, no, it doesn't. Thumbs. It does not form geometric isomers, guys. You see how there's two hydrogens here? If I swap the two hydrogens around, will it change the molecule? No, not a geometric isomer. Okay? That's why I refreshed you. Okay, so in this case, we're talking about an addition reaction. So we're going to break this double bond here, and we're going to add to it. I just need to check what it is. It says we're using hydrogen bromide. So hydrogen and a bromine. So when I break this double bond, carbon number 1 can either get another hydrogen or a bromine. Carbon number 2 can either get a hydrogen or a bromine. So that's when we're going to have to use Markovnikov's rule. All right? Markovnikov's rule works exactly the same as Zaytev's rule, just in reverse. So I look at these two carbons and I try to figure out which one's rich, which one's poor. So in this case, this one has 2 hydrogens. This one only has 1 hydrogen. Remember, we are only counting the hydrogens that are directly attached to that carbon. We are not counting these hydrogens. So this one is going to be the rich one. This one's going to be the poor one. And Markovnikov's rule states the rich get richer. All right? Which makes sense. You guys did the future finance course, so you would know if you have compounding interest, you're going to get rich if you have money already. So we break that double bond. And what it states is that the rich one that has the most hydrogens is more likely to get another hydrogen. So you're going to more likely get CH3, CHBr, CH2, CH3 as your product. This is, again, what we label as the major product because you're going to have that in a higher percentage. The other alternative is the minor product with the 2 flipped around. So every so often, you know, they win the lottery, the poor people, or they do some good investments. They've taken Ms. Garlick's future finance class, and so they now know how to invest, and the poor get rich again. So they, in this case, get the hydrogen. So you have CH2, 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 CH3, and the bromine's over here. This is the minor. Okay with that. It's just Zeta's rule working in reverse. Now, something to note that I don't know if I noted with Zeta's rule, if both of my carbons are the same number of hydrogens, I still have two products. It's just in a 50-50 ratio. You want me to write that down? Okay. Sorry. I'll let you guys copy that down. Yeah, so if they both had one, or if they both had two, then it's the same. Or if they both had zero, it's the same. Okay. And I'll show you guys the next example. Just mindful of the time because I'm going to go back to the thermal chemistry people. Not thermal chemistry, the energy people. All right, can I move it? Okay. So let's look at the second molecule they have for us. They gave us the same, no, different molecule altogether, not an isomer. But they put the double bond in the middle. So CH3, CH2, CH double bond, CH, CH2, CH3. Come back. Come back. Right, if I was to draw this in three-dimensional, or sorry, not three-dimensional, just draw it more extended. That's another way to look at it. All right, so again, another geometric isomer question. Can this one form geometric isomers? Yes or no? Yes, it can. Because you see how the carbons involved in the double bond have two different things attached to it? So that one does form it. All right, now, in this case, when we apply the addition reaction and we break this double bond and we add the hydrogen bromide, do you see here, I look at both carbons, they both have the same number of hydrogens. So they're both equal when it comes to rich and poor. Do we agree with that? Yeah. This one, however, is not an example of one that's forming a 50-50 ratio. There's only one product because this is a symmetrical molecule. So if I add the hydrogen to this one and add the bromine to this one, then when I form the molecule, I would get 1, 2, 3. So you see how I'm going to get 1, 2, 3, 3 bromo. 1, 2, 3, 4, 5, 6 hexane. All right? So that's assuming that this carbon gets the hydrogen and this carbon gets the bromine. If the opposite occurs and this carbon gets the hydrogen and this carbon gets the bromine, I would have CH3, CH2, CHBr, CH2, CH2, CH3. Do you see how this is still 3-bromohexane? 1, 2, 3. So I have the same product regardless. So in this case, there is no need to use Markovnikov's rule because it's symmetrical. Okay, so no Markovnikov's rule because that molecule is symmetrical. Yeah, that's how you spell Markovnikov's. I'm pretty sure that's how you spell it. I've been trying to think of ways to help me remember it because it's such a difficult name. Never sure where to put the V's. Are we okay with that so far? So that was that exam question. Just to show you guys the marking schedule so you guys are aware. What was this? Question 1? Zoom that up. Move. There you go. Close. All right, so you see here, achieve points, identifies the type of reaction, so this is an addition reaction, identifies there's 2 products formed for 1, but only 1 product for 3, explains why it's an addition reaction, explains the limited detail why there are 2 products, or correctly draws the structural formula, or identifies the major and minor products. So these are all merit points. The excellence then is the full explanation with possible organic products for both 1 and 3, and the structures must be correct. So that's what we're looking at for those points. And that's the proper write-up. Okay? All right. I think that's all. Oh, no, there's one more thing I want to say. So, like I said, in order to apply Markovnikov's rule, there needs to be 2 things that happen. First thing is that the molecule that you're using needs to be asymmetrical. So it should not be symmetrical. This is symmetrical, because if I cut it right here, it looks exactly the same on both sides. So if I have a molecule like that, that is symmetrical, so there's no Markovnikov's rule. The other thing to keep in mind is that Markovnikov's rule only applies when you're adding 2 different things to the organic molecule. So when I'm looking at Markovnikov's rule, it's going to be this one here, because in this case I can add a hydrogen and an OH, and in this one here you're adding a halogen and the hydrogen. So this is 2 different things being added to it. So both of those will need Markovnikov's rule. Okay? This one doesn't need Markovnikov's rule because it's adding 2 hydrogens. This one doesn't need Markovnikov's rule because you're adding 2 halogens. This one doesn't need Markovnikov's rule because you're adding 2 alcohols. So you're only using Markovnikov's rule here and here. Everywhere else, you don't need Markovnikov's rule. Does that make sense? So there's 2 factors that you need. Again, I'm pointing this out because potentially in the question, they might ask you to explain the requirements for when 2 molecules are going to form. So asymmetric carbon, or alkene I should say, and needs to be 2 different things being added to the molecule. If it's 2 of the same, then it doesn't matter. Both carbons getting the same thing. Cool? Questions, concerns, or comments from you guys? All right, that's us.